Hello everyone. Let's look at axial load and deformation in this video. So here we assume that the load is basically an axial load. It applies along the axis of the part, let's say a bar here. And so it can only do basically tension or compression. And the only effect it has is the change in the length delta. So we want to find a formula for delta, and we want to look at some problems where the properties of the material geometry can change along the way and so on, and look at a problem where the bar is statically indeterminate. So first thing is, how much is the change in the length? And here we assume that everything is happening in the linear region. So the elongation delta is equal to epsilon over L, because epsilon strain is delta, the change in the length over length. So cross multiplication, delta is, this delta is the same as the delta L, is epsilon times L. Now epsilon in the linear region is stress over Young modulus, correct? Because stress is E times epsilon. So epsilon is sigma over E, and sigma itself is P over A, right? So if you replace and simplify, your elongation is going to be PL over AE. That is the formula in the linear region. And clearly you see, the bigger the force or the bigger the length, the bigger the elongation, the bigger the cross section, which means thicker material, or the stronger the material, bigger E, that is going to be smaller elongation, which completely makes sense. Now this term in the denominator, A times E, is what we call axial rigidity of the bar. The bigger it is, the smaller the elongation is going to be. And it does completely make sense. Another term we have is called equivalent stiffness for prismatic bar in axial loading. So if you consider this equivalent to spring that is fixed on this end, and on this end you're pulling, and this is K or K equivalent, and this one will have the same delta. The question is, what kind of spring constant would that be? Well, you say basically the spring constant is equal to the force along the spring, which is P in this case, divided by the elongation delta. Now, if I divide P by delta, clearly you're going to get AE over L. So this is your spring constant. Okay? And this is basically the inverse of the spring constant, F over LE. So clearly you see, the bigger the axial rigidity and the smaller the length, the bigger the spring constant. Now this term here is the inverse of spring constant, and there is this technical term for it called compliance or flexibility. So if you hear the word compliance, that is the inverse of stiffness. Now, this is a very simple formula, PL over EA, and it assumes that everything along the bar stays constant. So P stays constant, A stays constant, and E. So it's one single material with one cross section, and the load is constant all over. But the matter of fact is, many times some of these properties can change. You might say, like what? Well, look at this example here. If you look at this bar ABC, this vertical bar, the cross section along the length of this bar is not constant. This here is A1, that is here is A2. And also, if you look at the axial load, you're going to see that the axial load is not going to be constant as well, because there is a pin here, there is pin reaction. So if you cut it between A and B or between B and C, the axial load is going to be different as well. So clearly in this case, you cannot use the simple formula. And so what you need to do is to break it into parts in which everything is constant. So you might say between A and B, the A is constant, the load is constant, the E is constant, and between B and C is a similar thing. And then consider these two to be basically two springs in series, where the equivalent is sum of them. And so you have one elongation here, delta 1, and you have another elongation here, delta 2. And the total elongation of this bar, delta, is going to be delta 1 plus delta 2. Okay? So basically, if you want to write it, your delta in general can be summation of I from 1 to n, where n is the number of sections inside which all of these parameters are constant. Okay, so if you add individual deltas, right, these are the individual delta i's. If you add them together, you can get your total delta. Good. So this is when we use it when some conditions are changing. Now, to practice using this formula, we are going to look at this interesting example here. So what I have here are two bars, A, B, C, and B, D, E, where at the end of C we have load P1, at the end of E we have load P2. The distances A, B, L1, and L2 are given, and everything is pinned. At D we have this horizontal bar pinned to the ground. At A we have the vertical bar pinned to the ground. The values for P1 and P2 are given. And along ABC, as I said, the cross section goes from A1 to A2, where A1 and A2 are also given to us. This is A2 and this is A1 in terms of inches squared. Also, length L1 and L2 are given. This is L2, this is L1. And A and B are also given in terms of inches. Now, the other thing is the material here. So they are made of steel, and the E of steel is 29 10 to the 6. This is not 106. This is 10 to the 6 psi or mega psi. And everything is made of steel, right? So the material is the same all over the place. And what you need to find is the vertical displacement at point C. So we need to find delta at point C, how much this point goes down, basically, based on this loading that you have. So what you need to do is to break this part into free body diagrams first. So this is the free body diagram of member BDE, and here we assume that the weights of the members are negligible. Okay, so it says disregard the weights of the bars and the beam, the bar and the beam. So then if you look at member BDE, at D and B you have two pins, and you might say, well, you might have two horizontal reactions. What happened to them? I'll explain. But let's first look at member AB. So there is load P1, there is and there is pin A, so there should be another reaction here, right? And the opposite reaction of that, action and reaction. So what are these values, right? Well, here, since this system is a static system, right? This system is static and it's not moving. So if I take total moment with respect to point A, clearly this horizontal force has to be 0. That's the only force that creates moment about A. And that has to be 0, otherwise this pin is going to start rotating. Now, when that force is 0, if I take some of the forces in the x direction, this force has to be 0 as well. That's why you see in free body diagram of ABC, only the vertical components exist, the horizontal ones are 0. Now, when B is 0, as we just found, if you look at the FBD of member BDE, this DE has to be 0 as well, because some Fx is 0. So again, in this one, the only forces are the vertical forces. So that's why you see no horizontal component in any of these two FBDs. Okay, I just first need to explain that before we move on. Good. Now, what are the unknowns here? The unknown is the reaction at D and the reaction at A. These two are unknown. P1 and P2 are given, and P3 is also unknown, right? That's a pin reaction. We don't know how much it is. Okay, we only have P1 and P2. Now, can we find them? Can we find them? Well, let's take a look. So in this FBD on the right, if you write sum and assume that the y-axis is upward and x is to the right, so if I write sum of the forces along the y direction for this guy, it's going to be negative RA and then plus P3 and minus P1. This is 0, clearly one equation with two unknowns. For this one, a similar thing, sum Fy, and for this one, sum Fy equals negative P3 plus RD minus P2 equals 0. So I got one more equation, but one extra unknown. Remember, P3 is unknown, RA is unknown, RD is unknown. So for this one, I have to also use the moment equation. So I go with some moment about the pinpoint D, and clearly if I go counterclockwise, P3 is counterclockwise times A, positive PA, P2 is clockwise, so negative P2B. This should be equal 0, and A and B are given, 28 and 25, and P2 is 5600. Now this one is clearly one equation with one unknown, and from here you should be able to solve P3 to be 5,000 pounds. There we go, because A, B, and P2 are given. Now that you got P3, guess what? I can plug it into these two equations, and I should be able to find RA and RB. Not that I need RD, not that I need RD, but I can find it. What I really need is RA, because RA is going to affect the displacement at C, which is what I care about. So if I plug it here, clearly you see RA is going to be P3 minus P1, and P1 is 2100, and this one is going to be 2900. And again, I can solve for the other one, that is going to be P2 plus P3, right? And that is going to be 10,600 pounds. Which again, I don't care about this one, but this one is important, this RA 2900. So now that I found my unknown reactions, it is time to look into the formula that we just learned, this one. And for that, we are going to look at this member ABC. Now, if I look at member ABC, there are two sections to it. One section is this, the other section is this. What's the difference between them? One is their cross sections are different. The other one is the internal force in them is different. And of course, each one has a different length too, but between them, force and cross section is different. Now, both are from steel. So what I can say is, I can say delta at point C, which is what I care about, the total elongation of this member, because the other end of it is fixed. So the total elongation of this member is going to show itself at C because the other end is fixed, right? This is equal to delta of member AB plus delta of, not member, portion AB and delta of portion BC. If I can find these two, I'm good. Now for member AB, what I need is the force in AB. So let's call it, if I want to go with this formula, it's going to be N, the axial load in member AB, times length of member AB, which is L1 in this case, divided by cross section of member AB, which is A1, and the Young modulus, which is E. And for the other one, it is going to be the normal force in portion BC, length of it, which is L2, divided by cross section, which is A2, and again the same E. So if I add these numbers together, I should be getting my values. And A1 and A2, E, L1, L2, they are all given. The only thing not given are the axial forces in them. To find them, we need to cut these members. So here I'm going to go and cut this member, portion BC. If I cut portion BC, I'm going to get two sections. I'm going to get this portion here, and I'm going to get this small portion here. So this is B, this is A, this end is C. I cut it somewhere between B and C. And this is the load here. This is that N of AB or BC. And how much is it? Well, I can look at the FBD of one of these sections. One of them, doesn't matter. So I can look at this right-hand side here. The only force that is down applied on this one is P1. If I want to do the other one, then I have to not only plug in RA in it, I also have to plug in P3 in it. And the result is the same. It doesn't make any difference. You calculate from either one. Clearly, NBC is going to be equal to P1. Right? It's obvious here. Sum of y equals 0. So this one is P1, done. Now, if I cut it here between A and B, again, I'm going to get two portions. One portion is this, where this point is A. The bottom portion is going to be something like this. So this is B, this is C, this is P1, this is N of AB, this is the reaction RA, and then that P3 is going to be right here. So I can use any of them again here, and if I use the left side, one this time, you clearly can see that NAB is equal to negative RA, again sum Fy equals 0. So this one is negative RA. That's all it is. So then go ahead and plug in the numbers. You see, that's where I need RA. So RA is 2900, so it's going to be negative 2900. And then we have L1, which is 20 inches. And I'm going to write down everything in inches. And A1, the first cross section is 1/4 inch squared. And E is 29 e to the 6. And pay attention to your units. This is inch squared. This is pound per inch squared. So this bottom portion is going to be just pound and pound simplify. You get it in inches. And P1 is clearly, we have P1, right? 2100. And L2 is 34.8. And then A2 is 0.15. And E is the same number. So if I simplify, I will get 0.0088 inches. That is how much the bottom of point C is going to go down. Okay, so you see that how we use the formulas we learned in statics and the one we just learned for axial deformation of solid mechanics to solve this problem here. Okay, now sometimes the formula we just learned cannot be applied because the formula I just showed you is assuming that the changes in those parameters N, A, E, or L happens in a kind of step type behavior. So it jumps from this cross section, right, to this cross section. Okay, so it's a sudden change. It's not a gradual change, but the matter of fact is sometimes the parameters are changing gradually. Like for instance, you might get something like this. The cross section is constantly changing because the beam or the rod in this case is a conic shape. So A, the cross section, is a function of location. And even if the load is constant on it, clearly A is not going to be. Now, maybe your force is also not constant along the member, or it could be along the member. But in general, what you need to do is to consider an infinitesimal element along the rod with length dx at location x, and then you find the infinitesimal elongation for that element, which is the force, the axial force at that location, n of x, times the length of it, dx, divided by e over a of x, and then integrate all of these infinitesimal elongation from 0 to L. Now here, assume that E is constant all over the material. Okay, if E is also a function of x, then you do E of x at the denominator. But most of the time, the one that is really variable is this A. And you have to integrate this. So just pay attention that not every time that summation is working. And if it's a gradual thing, summation will be converted to integration because you have infinitely many of these terms. Okay, now another thing that we can solve with this new formula we learned is sometimes we have axial loading systems like this, and the system is statically indeterminate. Like if you look at this beam here with three cross sections, A2, A1, and A1 on the other side, and the loads on the middle section are PB and PC, right? And these numbers are given for PB and PC, and cross sections A1 and A2, as well as the length L1 and L2, everything is given here, right? So we have everything here. And what we need to find is first the reactions at the two ends, reaction RA and RD, what are they? And then the compressive axial force FBC in the middle segment. So you know this middle segment is clearly subjected to compression because we are pressing on both sides of it. How much is that? But in order to find it, first we need to find the reactions on the left and on the right side. And the problem is, if you draw the FBD for this member, guess what? It is statically indeterminate. Why? Because let's draw the FBD. Now both sides are fixed, so clearly you can consider three reactions on each side, but here the system is perfectly horizontally loaded. There is no vertical load. Again, we are neglecting the weight of the bar here. So it's not mentioned, but we are neglecting the weight. So there is no vertical load. Since there is no vertical load, I do not need any vertical reactions at the ends. And since there is no vertical load, there will be no bending. So no bending moment is needed. Therefore, the only reactions that you need on the two sides are two horizontal reactions in this case. So what I need is one reaction here, which I can call it RA, and another reaction here, I can call it RB, which are both unknown. Now, clearly, if you write your equation in the x direction, you only get one equation, which is RA plus PB minus PC plus RB equals 0. You see one equation with two unknowns. That's statically indeterminate. So what can we do now? What we can do is to look at the deflections that we have, or in this case elongations, at these endpoints. These endpoints are fixed. They cannot have any elongation. So if we say that the elongation, the total elongation of this total beam, the total elongation is 0 for the whole beam, or in this case the rod, that means these parameters, these four forces, have to have a relation with each other. So how do we solve this problem? This is how we do it. We say that this rod is, we release one of these ends that is fixed, we say that, let's say it's fixed at A, but on the other side, we say that it's not fixed, we let it move, we take the support away, but instead of the support at D, we put the effect of it, which is R of D. By the way, this is R of D, not B. Okay, this is point D. So we show it like this. This has the same effect. We took away the support, but showed the effect of it. But this left side, we kept it fixed. Okay. Now what? We go ahead and calculate the total elongation of this rod here. And remember that PB is here. And remember that PC is here. So we calculate the total elongation of this, and then we set it equal to 0. That should give us an extra equation. So if you look at the rod here, there are 3 sections: section AB, section BC, and section CD. And they have different length, different cross sections, and there will be different internal loads. Since I have 3 sections, I will use this formula that we just learned with 3, n equal 3, and I will get the total elongation of this rod. So the total elongation of this rod equals delta of section AB plus BC plus CD. Now, what is it for section AB? It's the normal force in section AB, which we have to find, times the length of member AB, which is L1, divided by cross section of it, which is A1, and this Young modulus is the same for all of them. The same goes for BC. The length of it is L2, the cross section of it is A2E, and finally n of CD, L1, A1E. And sum of that total thing should be equal to what? To 0. Now, clearly, since E is the same in all of them, we can get rid of it. A's and L's are given numbers. The only thing we need to find are these ends. To do that, we need to cut the rod like last time. So if I cut it between C and D, I get a right side and I get the left side. And I prefer to use the right side because it has fewer forces on it. So on this side of it, I have RD. And on this side of it, I have the normal force between C and D, or the axial force, basically. Clearly from here, you see that NCD should be the same as RD. Done. This is the first section. Then I cut here between B and C. If I cut between B and C, again, you have a left side and a right side. Up to you which one you want to cut, you want to consider. So here, again, I go with the right side of it. If you look at the right side, this is what you have on the right side. You have PC here. You have R of D here. And you have this normal force CB or BC. And writing the total forces in the x direction, clearly NBC is going to be RD minus PC. Okay, so we found this one. And finally, we cut between A and B. If you cut between A and B, again, you have a left side and a right side. This time I would look at the left side of it. And on the left side, we have this axial force NAB. And on this side of it, we have that reaction that we just had, RA. And clearly, looking at these two, NAB has to be negative RA. Now, if you look at this, clearly, this is an equation. PC is a given number, so it's a relation between RA and RD, the two unknowns. and this top one was another relation between them. So ideally from equations 1 and this equation 2, I should be able to solve for my unknowns. If you look at equation 1, you will get RA plus RD. Again, this is D, not B. Take the other two numbers to the other side, you get PC minus PB. And the numbers for C and B are given, 17 and 25 and a half. So 17 minus 25.5, so you get negative 8.5 kilonewton. That's the first equation. And the second one here, we have to the coefficient for RD is L2 over E, right? So it is going to be something times RD. There is this coefficient for it, and there is also this coefficient for it. So what I need to add is L2 over A2 plus L1 over A1. So 0.4365 is the coefficient for this. And then for RA, that is the coefficient with a negative sign. So just L1 over A1, which is 0.2381. And then this L2 over A2 PC is going to go to the other side and become positive. So that is going to be equal to 3.373 kilonewton. And this is clearly a 2x2 system of equations. And I bet everybody can solve for both of these unknowns. So if you do so, your unknowns are going to be, so if I just use a small approximation, this is going to be negative 10.5 and this is going to be negative 2 kilonewton. 10.5 and 2. Now this is positive 2, not negative. Now, would they hold to this here? So you can always go back and do a sanity check. This is negative 10.5. This is positive 2. This one was 17. And this one was 25.5. So if you subtract, that is a 15 plus 2, 17 minus 17 is 0. So you see clearly that these are the correct reactions. There we go. So we found the reactions on both ends, and we answered part A of this problem. Now it says, how much is the compressive axial force in the middle section? Remember, in the middle section, the compressive force, or the force, is NBC, and NBC is how much? RD minus PC. So let's write it. Well, RD is 2, PC is 17, so we get negative 15 kilonewton. And that is the compressive force in the middle section. Done. Okay, so this is how we solve for this problem using the elongation formula. And so you see, when the problem is statically indeterminate, it doesn't mean if you bring in solid mechanics, you still cannot solve. So when a problem is statically determinate, we have to use solid mechanics, and we use the deformations information from solid mechanics and look at the boundary condition, see which ones can move, which one cannot, how much they can move. So plus boundary conditions, then you can solve them. Although in statics you couldn't, now with the extra information that you have in solid mechanics, you're able to solve this kind of problem. And we're going to do more of that when we look at other scenarios like beam bending or torsion of the shafts and any other scenario, we're going to look at more indeterminate problems that were not solvable in statics, but now they are solvable using the extra info of solid mechanics. So hopefully the video was useful to you. I'll see you in the next video.